You know, when you hear a sound or a radio signal flies through the air, what is it really? Well, everything like that has a hidden recipe. It's a unique mix of pure, simple frequencies that all add up to create the complex signals we experience. And today, we are going to pull back the curtain on the amazing tool that reveals that recipe, the continuous time Fourier transform.
Okay, so let's start here. We already have a fantastic tool for signals that repeat over and over again. You know, like a perfect, sustained musical note. It's called the Fourier series. But here's the thing. Most signals in the real world just don't do that. Think about a clap of thunder, or you saying a single word, or one beat of a drum. They happen, and then they're done. They're one-time events.
And you can really see the difference here, right? On the left, you've got that predictable, looping signal. Easy enough. But on the right, that's the real world. It happens once, and it's over. These two things are fundamentally different, and figuring out what's inside the signal on the right, that's a whole different challenge.
So that brings us right to the big question. How in the world do we take these finite, real-world signals and figure out their frequency recipe? How do we see their spectrum? Well, the answer comes from this incredible moment of insight from Joseph Fourier himself.
He came up with this brilliant little mental model. I just love calling it the infinite period trick. It's a mind-bending leap in logic that beautifully connects the world of repeating signals to the world of these one-off, non-repeating ones.
Okay, so here's the big idea. Just imagine that one clap of thunder. Now, what if you pretended it was part of a repeating pattern, but the next clap wasn't going to happen for, say, 1,000 years, and the one after that, another 1,000 years? Well, if you stretch that time between the repeats all the way out to infinity, all you're left with is that one single event. You're basically tricking the math by treating a non-repeating signal as just one cycle of a repeating one with an infinite period.
So let's actually watch what this trick does to the frequencies. For a normal periodic signal, with a period we'll call t, the Fourier series shows us its frequency ingredients as these separate, spaced-out spikes. Each spike is a specific frequency, a harmonic.
Now watch what happens when we double that period in the time domain, making it 2t. Look at that. The frequency spikes get twice as close together. It's like we're getting a more detailed, denser picture of the frequencies that are hiding inside.
And let's do it again. We'll increase the period to 4t, and yep, a really clear pattern is showing up. The longer we make the period in time, the closer and closer those frequency spikes get. They're actually starting to trace out a very specific shape, aren't they? An envelope is starting to appear.
And here is the punchline. This is where the magic happens. As we push that period t all the way out to infinity, I mean literally to infinity, the space between those spikes goes to zero. They get so incredibly dense that they just merge. They transform from a bunch of separate lines into one smooth, continuous curve.
And this continuous curve, this beautiful envelope that we just discovered through this thought experiment, well, it has a name. It's the frequency spectrum of our non-repeating signal.
And the tool that actually calculates this for us is the Fourier transform. It is the math that formalizes that whole infinite period journey, giving us the exact shape of this continuous frequency spectrum for basically any signal you can imagine.
Now don't get scared by the math here. Let's just talk about what this means. The top equation, that's the analysis machine. You put your signal from the time world, x of t, into it, and it spits out the frequency recipe, x of j omega. The bottom one, that's the synthesis machine. It does the exact opposite. You give it the recipe, and it rebuilds the original signal for you. It's this perfect, beautiful two-way street.
Honestly, the best way to think about this is like a prism. You know how you shine white light into a prism and out comes a rainbow? The Fourier transform does the same thing for signals. You feed it a complex signal, and out comes this beautiful spectrum, a rainbow of all the pure frequencies it's made of.
Okay, so theory is great, but let's build some real intuition for this. Let's look at a few really common signals and see what their frequency spectra look like. You can think of it as a little time-to-frequency dictionary. First up, a simple rectangular pulse. It's like a switch that's just flipped on for a moment, then flipped off. You'd think it's pretty simple, right? But look at its frequency spectrum. It's this wavy, decaying shape called a sinc function. It turns out, to create those perfectly sharp, instant edges of the box, you actually need an infinite number of frequencies all playing together in a very specific way.
Okay, get ready for a really mind-bending one. This is a unit impulse. It's an infinitely short, infinitely intense spike that happens at just one single moment in time. So what's its frequency content? Everything.
all of it, a perfectly flat line. This tells us something profound. To create a perfect pinpoint in time, you need every single frequency in the universe all contributing with the exact same strength. Kinda wild, right?
So what all of this shows us is this fundamental trade-off, almost a law of nature. The more you try to pinpoint a signal in time, like that really narrow impulse, the more it spreads out and gets wide in frequency. And it works the other way too. A signal can be short in time, or it can be narrow in frequency, but it can't be both at the same time.
But, okay, why does any of this really matter? Why is this such a big deal? Well, this transform isn't just for looking at pretty spectra. It has some incredible, let's call them superpowers, that make it one of the most important tools in all of engineering and physics.
And here it is. This is its most famous superpower. In the time domain, if you want to filter a signal, you have to do this really complicated, messy bit of math called convolution. It's a pain. But in the frequency domain, it becomes simple multiplication. That is a complete game changer.
So, in practice, here's how it works. Instead of that messy convolution, you just follow 3 easy steps. 1. Transform your signal and your filter. 2. Multiply them together. 3. Transform the result back to the time domain. That's it. You've turned a really hard calculus problem into simple arithmetic. It's amazing.
And this superpower is also the foundation for basically all of modern communication. It's how radio works. By multiplying a low-frequency signal, like your voice, with a super high-frequency sine wave, we can literally shift your voice's entire spectrum up to a radio frequency so it can be broadcast. That whole process, called modulation, is a direct application of the transform's properties.
All right, so let's just quickly recap the big ideas here. The Fourier transform is our prism, our DNA sequencer for any signal that doesn't repeat. It comes from that brilliant little idea of a periodic signal with an infinite period. Its absolute superpower is turning nasty convolution into simple multiplication, which makes things like filtering possible. And finally, it reveals that deep, inverse relationship between how long a signal lasts and how wide its band of frequencies is.
And that leaves us with one last big thought. The Fourier transform shows us that any signal, any sound, any wave, it's all just a recipe of frequencies. This means we're not just limited to analyzing signals, we can build them from scratch too. So the question is, now that we have the power to mix and match any frequencies we want, what new sounds, what new images, what new signals can we build by just changing the ingredients?